I'd like to thank everyone who's joining us today. Welcome to CNCF's webinar today, Storage Landscape for Containerized Stateful Applications. My name is Sheila Faby, CNCF Ambassador and Open Source Program Manager at Comcast, and I'll be moderating today's webinar. We'd like to welcome our presenters today, Alex Kirchhoff, Founder and CTO of Storage OS, Luis Pabon, MTS Engineer at Portworx, and Xing Yang, Lead Architect at OpenSDF. A few housekeeping items before we get started. During the webinar, you're not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there, and we'll get to as many as we can at the end of the presentation. With that, I'll go ahead and hand it over to Alex, Luis, and Xing and to kick off today's presentation.
So I guess good morning, good afternoon, good evening, depending on where you are. We'd like to talk to you today about a white paper we've written to discuss the storage landscape in cloud-native storage environments. The three of us are members of the CNCF Storage SIG, and further details about the Storage SIG are available on the CNCF website. So we originally started putting together the content for this storage landscape white paper around this time last year. And what we wanted to do was to capture information that would provide the tools that are necessary and the understanding that's necessary for developers and DevOps teams and infrastructure teams that are working in cloud-native environments to fully utilize cloud-native storage. And why is, ultimately, why is storage important? So the bottom line is we don't have, there's no such thing as a stateless architecture. Every application needs to store some sort of state somewhere. And that can be, that system that stores the state can be something that's running in your cloud native environment, or it could be an external component of your infrastructure, or indeed a service that's running in the cloud. One of the things that we want to focus on is that there's a lot of effort to containerize applications, and containerizing applications does enable portability of the application. But it doesn't necessarily enable the application to be completely portable because, as we said, all of those applications need to store state, and the state and the portability needs to move with the applications. So kind of moving away in the cloud-native storage environment, we're moving away from storage systems that are presenting storage or utilizing storage in VMs and operating systems and hypervisors. And we're moving more to an application-centric view of storage, where storage is consumed and presented and utilized by the applications, which in themselves are portable. And of course, interoperating with storage increases the ability to deploy more complex cloud-native applications and allows better portability across different environments, whether it's on-premise or in the cloud. So the storage landscape white paper, there's a link to it there, and it's also listed in a PDF form in the Storage SIG GitHub page. Allows us to define what makes up a storage system. So effectively it gives us some basic working tools to say, this is what a storage system is made of, and these are the terminology, the different terminologies that are used when defining or utilizing different components in a storage system. So this includes the different layers of a storage solution, the way you can access a storage solution, as well as the different management interfaces that are used when orchestrating cloud-native storage solutions. And the reason why we put this paper together is to give users who may not have a lot of storage expertise the ability to choose the right type of storage system for themselves. So for the longest time, storage used to be one of those things where you just used whatever was available in your organization. But with cloud-native environments, developers now often have a much richer choice of applications, of storage solutions, which means that they can now choose storage solutions that fit the application rather than trying to fit the application around the storage system. So inside the storage solution, we already discussed, there are a number of different interfaces, and each of those interfaces are probably better optimized for specific use cases. And often we have a number of different layers of functionality which will be utilized in the different storage systems, and that functionality provides the different attributes that we measure a storage system by. So things like availability, scalability, performance, consistency, and durability. We'll be talking about the white paper and also some of the ways that we interact with cloud native storage in the Kubernetes environments today. So these different storage attributes can be measured across a number of different axes. So when we talk about availability, sometimes we're talking about the failover or the redundancy capability of a storage system. But it can also mean, it can also refer to the different ways of protecting your data in a storage system, or the ability of moving the data between nodes when nodes fail, for example. Similarly, scalability can be measured in a number of different ways. Sometimes it's simply about the number of clients that it can support, or indeed the number of storage operations per second, or the throughput. But sometimes it's also about the ability to add scale to the storage system by adding components in a horizontally distributed fashion. Similarly, performance can have different meanings. We can have performance measured in terms of latency, for example, which might be really important in terms of a transactional system. But it can also be measured in terms of throughput, for example, if we're dealing with things like data analytics or large quantities of data that need to be processed. One of the things that is a topic which often comes up in cloud-native storage solutions is the concept of consistency. So consistency is a factor that that arises by virtue of the fact that a lot of cloud-native storage systems are distributed in some form and have some sort of scale, and therefore need to consider how data is made consistent across a number of different nodes. So effectively, consistency can be measured in two ways. One, in terms of the amount of time it takes before the data that you send to the storage system is actually stored on physical storage. But it's also the amount of time that it takes for data to be queried by another system once that data has been committed. And then finally, there's the concept of durability. So durability is different to availability, because what we're looking at here is the concept of how many failures can happen, and what type of physical parameters are in place that actually protect your data. So things like data protection have some level of commonality between availability and durability, but it's also more things like the number of, for example, different regions or different locations where your data is stored. So the ability to tolerate failures and still retain and store the data. Of course, as we mentioned, cloud-native storage systems can take a number of different forms. And apart from the attributes we just discussed, the way you instantiate and deploy a storage system has a large portion, plays a large portion of how those attributes are affected. So You obviously have hardware solutions which are installed in data centers and are probably what a lot of people are familiar with today. There are also software solutions which go a long way to making the storage system more portable, because it means that the software can be deployed in a variety of different platforms. Some storage systems that are software defined can also be deployed as a container, and therefore can be better automated by an orchestrator. And of course, finally, all of the different storage systems and solutions that we're talking about today can typically be consumed from public cloud providers too. So the storage services can be consumed without actually deploying your own storage system, if that's where you want to go. So we looked at the different types of storage environments, and we kind of grouped the storage systems based on data access interfaces into two main buckets. The first bucket being volumes, which is possibly what most people are more familiar with when talking about storage. So things like file systems and shared file systems and block devices. And volume interfaces are what's very often consumed and orchestrated by an orchestrator. So it's probably fair to say that a lot of the development in orchestrators has been around providing the capabilities for automating volumes. In another bucket, we have what we've called API-driven storage. So this covers all the other types of storage, like object stores or key value stores or even databases, where you can obviously store state, and you can run and you can use those systems to as the backends for your applications. But obviously, they tend to be accessed over over an API. Now, again, there is some work ongoing in a number of different projects that are providing some capabilities to orchestrate abstractions around some of these API systems. But it's probably fair to say that the volumes are the more mature solutions today. So when storage systems are compared, very often the data access interfaces define a set of attributes for that storage system that actually provides the capabilities that actually define the capabilities of a storage system. And this is often because the way you access the data affects things like availability or the ability to failover, or perhaps performance or latency capabilities. One of the things that we discuss further in the document, however, and this kind of provides a segue to the next section of our presentation, which Xing will cover, is that nowadays storage systems often have a number of different layers. And it's probably no longer fair to define the attributes of a storage system just by the data access interfaces. So for example, there are many file systems which are built on top of an underlying object store. So for example, that would mean that it could have file sharing capabilities across multiple workloads because it's being accessed as a file system, but it might have throughput or latency or scalability attributes of the underlying object store. And with that, I'll pass the baton to Xing, who can talk about the storage layers in a storage system.
Thanks, Alex. So there are several storage layers listed here that can have impact on attributes of storage systems. Next slide, please. There are layers overlaid on the data access interfaces as part of orchestration that could also affect availability, scalability, and performance. For example, rather than directly access resources, a hypervisor can provide access to resources by performing functionalities such as mapping, pooling, resource management, and so on, and that could add access overhead. Next slide, please. Storage topology describes the arrangement of storage and compute resources and the data link between them. This can affect availability, scalability, performance, and consistency. In centralized topology, there are usually a few nodes that are tightly coupled with each other. This is usually used in vendor-specific hardware-based storage solutions. It supports scale-up. It is more consistent with low latency compared to distributed storage systems. This is used in many block-based storage systems. Storage systems using distributed topology usually has a focus on software solutions. It uses a software solution on commodity hardware. It's usually implemented using the shared nothing architecture and needs to synchronize across multiple nodes through network connections. It can scale horizontally with more nodes and more clients. It is also more complex to operate. Sharding is usually used in database applications while datasets are partitioned. It can scale horizontally, but it can also add operation complexity. In hyperconverged topology, storage and compute resources are deployed together on the same node. Multiple nodes cluster together to form a resource pool. In this topology, we usually have a software storage solution on commodity computer nodes. So this is similar to many distributed systems. In this case, storage nodes can grow together with compute nodes. But there's also downside, and there's a tight coupling between compute and storage. So failure on the compute nodes also means failure on storage systems. Next slide. So this table shows the comparison between local, remote, and distributed systems. So for local systems, availability is limited by components locally, and scalability is limited by local architecture. It can achieve consistency easily, and the durability and performance are both limited by local components. Some applications may benefit from the low latency of local systems. In remote systems, availability may be limited by single point of failure, and scalability and durability are limited by monolithic architecture. And we can also have consistency, but it is harder to implement compared to local systems. Performance is similar to local, but it also depends on network. In distributed systems, we can have high availability because clients may have access to numerous nodes. And we can have scalability by adding additional systems. And durability and performance can also be increased by adding additional systems. We can achieve consistency, but the implementation of consistency is the hardest among these three different systems. Next slide, please. Storage systems usually have data protection layer, which adds redundancy. This refers to RAID, erasure coding, and replicas. RAID uses different combinations of striping, mirroring, and parity techniques. Striping means data distributed evenly across two or more disks for improved performance. And in mirroring, a mirror maintains identical copies of datasets across two disks, so that requires more space. In parity, a dataset is distributed across a number of disks that are grouped together. For each unit that stores data, typically a block, an algorithm is used to generate another set of parity. So that will add more redundancy, and also that saves the disk space compared to mirroring. And RAID is usually used in the same node, but it is also used in distributed systems across nodes. For erasure coding, a data set is split into multiple fragments, and each fragment is encoded and then stored with a configurable number of redundant parity sets. So that is used to optimize capacity, durability, and redundancy. But that will also add computational overhead, and it will add latency. This technique is used in distributed systems, and also it is the main building block of many object stores. Replicas refer to mirrored data sets distributed across multiple nodes. A replica is a full copy, so it is very fast to recover from failure. It has lower computational overhead and lower latency. Next slide. Storage systems usually provide data services in addition to core storage functions. So that refers to replication, snapshots and clones, and encryption. Replication involves primary and secondary storage. It can have 2 or more sites. It can support sync or async mode. In sync mode, we can have stronger consistency, but it is limited by distance. For the async mode, it can support longer distance, but we need to have a bandwidth that is guaranteed so that data can be transferred in the acceptable amount of time. Replication usually has requirements for RTO and RPO. RTO refers to how soon you can access to an alternative replica when failure occurs. And RPO refers to the duration of the amount of source data that can be lost on failure. Snapshot is a point-in-time copy of the data set. A snapshot can be used to restore the original data set when needed. Snapshot may or may not be dependent on the source after it is taken. This depends on the underlying storage systems. It usually uses a copy-on-write technology, which is space efficient. Clone is a full copy of the data set, not dependent on the source. A snapshot is usually read-only, and clone is usually read-write. Encryption can also be applied to ensure data security. It can be implemented on data in transit or data at rest. Next slide. Storage systems ultimately needs to persist data somewhere on a physical layer, which is usually non-volatile. This has an impact on overall performance and the long-term durability. There are traditional spinning disks that are low in cost with regard to capacity. There is SSD with the traditional interfaces, so that can provide a lower latency, but throughput is limited by the transport. NVMe is a new transport that is very fast and designed for flash, and that can be used to achieve lower latency and much higher throughput. Next slide. Now let's take a look at the orchestration and management interfaces. This diagram shows workloads consume storage through data access interfaces. There are 2 ways for storage systems to interact with the container orchestration systems. The darker green box here, control plane interfaces, refer to storage interface directly supported by container orchestration systems. That includes CSI, DVDI, Flex Volume, and native Kubernetes drivers. This interface is focusing on storage provisioning, such as dynamic or static provisioning. This orange box here, called frameworks and tools, is actually an extension of control plane interfaces. In addition to provisioning, this interface could also provide functionalities such as discovery, automation, data services such as data protection, disaster recovery, data migration, and data lifecycle management, also monitoring, analytics, performance tuning, and so on. We will be focusing on the control plane interface here in this darker green box. There are Kubernetes in-tree volume drivers that support block and file systems. There is a Docker volume driver interface that supports volume provisioning. Flex Volume is an out-of-tree plugin for Kubernetes. Because Kubernetes SIG storage is moving towards a CSI, Container Storage Interface, so new features will only be added to CSI, not to Flex Volume, not to the in-tree drivers. The Container Storage Interface, CSI, is an industry standard to define a set of storage interfaces so that a vendor can write one plugin and have it work across a range of container orchestration systems. CSI has 3 gRPC services: controller, node, and identity services. Identity service provides information and capabilities of a plugin. Controller service supports create and delete volume, create and delete snapshot, and attach and detach volume. Node service supports mount and unmount volume. Expand volume support is also added to both controller and node services. So that's an overview of orchestration and management interfaces. Now I will hand it over to Luis, who will talk about storage for stateful applications.
Thank you very much, Xing. And thank you very much, Alex, also for the great introduction. So as we've learned how storage is defined, and we have learned about volumes and block and file specifically. Also, we have learned how these set of storage systems interact and are defined with the container orchestration system. So I will be diving into exactly how it works in Kubernetes. So normally what we have here is, before I jump into containers, I want to talk a little bit about virtual machines. And in virtual machines, what we have, if you're coming from there, we have a system where we have a hypervisor being run on some host, and the hypervisor is the one that's managing a lot of the storage system. So I just want to keep that in mind, that the host itself may not be able to, may not have the interaction with the storage, but normally it's the hypervisor who's providing these services to applications. Unlike that, in hypervisors, containers work a little bit differently, and I'll be diving into that. So the way it works in Kubernetes is that first, an administrator is managing the storage system. They understand what storage systems they have. They have connected to it. They have made it available, and now they want to make it usable for their users. What they do first is that they find a set of storage classes. These storage classes have a set of definitions specifically for their storage system. And then they name these storage classes whatever they want to. For example, in this example, we have a fast storage class, which may have parameters that be sent to the storage system to create fast storage, maybe using NVMe. And then we have a slow named storage class, which may have parameters that are be sent to a storage system to create maybe storage instead of NVMe, but from slower storage devices like spinning media. So the next slide shows a user being able to then request storage. Requesting storage in Kubernetes is called a persistent volume claim, okay? So the developer says, I want a persistent volume claim, which is going to consume storage from the fast storage class. When this is then submitted into Kubernetes, and Kubernetes then goes through a set of services, first trying to define what storage class you mean. Oh, this storage class called fast. This storage class uses this specific storage system. And it sends a command to that storage system, either through the in-tree, the older model, or through CSI, which is a newer model, to then go ahead and create that volume to satisfy the requirements from the persistent volume claim. When that happens, the storage system then goes ahead and creates a volume for that. That volume then is the volume ID, or the volume information, is then returned to Kubernetes and says, here, Kubernetes, here is the volume you asked me to create, and here's the ID for it. That ID is then taken and saved in what's called a persistent volume, and a different object, which is cluster-wide. That persistent volume object is, in other words, some metadata that describes information about where the volume ID and which volume actually services that volume ID, while the persistent volume claim is the request from the user. Next slide. So once we have both the persistent volume claim, which is again from the user, a request, but which points to a storage class, and the persistent volume object, which describes the volume, the ID, and the driver that it uses to manage this volume, a binding occurs. The binding occurs, and in Kubernetes, when you look at, for example, you say kubectl get PVCs, what you're looking at it's your PVCs being bound to a persistent volume. Again, that's a one-to-one correlation. You cannot have one persistent volume to many PVs. You can only have one PVC, meaning a persistent volume claim, to one persistent volume. So why is it that you have this type of binding? Let's go to the next slide. And that is because the life cycle of the volume that is requested. So now with that information, when a application refers to a persistent volume claim, that claim points automatically to the actual volume that services it. With this information, Kubernetes has now a life cycle for this volume. When an application is placed on a node, it first has to look at the application persistent volume claim, which then points to the persistent volume. And then it says, oh, this is for this specific storage system. Here's the ID of this volume. I want you to do the following. For example, if the Kubernetes is deploying an application on a specific node, it will first want to attach that volume to the node so that the application can get access to it. Once it's attached, meaning that the volume, it has if you know Linux, it now has a device node on the host. It is then asked to mount it to a specific location. We'll go into mounting and attaching in a second. But the life cycle is that Kubernetes, when it deploys an application, it first wants to attach it and then mount it. And then at that point, it's then consumable by the application. Once the application gets either evicted or gets moved for some other reason to another node, it will get then unmounted and then detached from that host. And then it will get reattached to another node where the application is moving to. Or in a situation where the application is being deleted and the PVC is being deleted, the application is removed, the volumes detached, are mounted first, and then detached, and then a command is sent to the storage system with the ID in the PV saying delete this volume. Okay? All right, let's go to the next slide. So now let's go through a little slide demo of exactly how is it that storage gets mounted into the system. The very first thing that happens when an application is chosen to go into a node, the application's first, we have to somehow go into the scheduler, has to define where, in which one of the nodes, the many nodes that Kubernetes has, is the application going to. There's multiple ways of doing that. We have, if the Kubernetes method is one way, there's other methods to extend the scheduler of Kubernetes to be able to have a smarter way to determine which node to put the application onto. But in one way, in another, a node needs to be chosen somewhere on the cluster to place the container to run the application. Once it has been chosen, before the application gets placed on there, the next slide, please. Next slide. The controller tells the storage system to attach the volume to that specific node. Once that happens, a device node gets created on that node. And here's what's a little bit different than virtual machines. In virtual machines, you have the ability in the hypervisor itself, think of it in QEMU, KVM style, that it has the drivers to be able to talk to your storage system. But in container world, it is very important to note and remember that it is the host system that needs all the drivers and the ability to attach to your storage system. So if you're asking for iSCSI or Fiber Channel or some other custom model, all that information needs to be part of the host, either a privileged container or part of the host itself. Either way, a device node needs to be created on the host itself so that the kernel of the host knows about this device. Second step is, next slide, is that now that the host has that attachment, the kubelet running on that node needs to send a message to the storage system saying, okay, now that the host has the attached device, we need to mount that to a specific location. And it gives the location to the storage system driver. It says, I want you to mount it here. So the storage system driver then mounts that location on their var lib kubelet and some other hashes and things like that for that node. So next slide. Once it is mounted in that location, it is mounted on the host. So if you think about it, before we even get to the container, before we get to the application, the host itself has the information. It has the volume attached and it has the volume mounted. But to run that inside a container, we need a third step. Container runtime systems have a model of taking a host directory and mapping it inside a container. And that's called binding. You do that through a mount bind. So in this model, what we have here in this example on our slides is that we have that the kubelet has the mount point servicing the storage system because it was attached to this node, but now the container runtime system, Docker, Rocket, something else, can then take that mount point and map it inside to the container, meaning like if you want /data on you specify that on your YAML inside the container. So that's all done by the container runtime system, which in itself it's communicating with the Linux kernel to be able to do all this. Okay, next slide. So in summary, what I just described can be done for block devices, meaning if you put in the PVC, that's called read-write once, and that's an exclusive access to that volume. But sometimes you may want multiple access, meaning many nodes or many applications are being able to access that storage. So for those models, we use the read-write many, which creates a file system. And with that model, you go through the same process, but now you can mount it and attach it and mount it on many nodes. And also, you also have the models where these applications can come up, and instead of accessing through the kubelet, through the host, you access this through APIs. And this is what we said before, Alex said before, and so did Xing, that you can access object stores or databases through their own APIs through the network. Next slide. So now that we have all this explanation, now that we described how storage works, how it is defined, how it is divided into different sections, how it is consumed by container orchestration systems, we're asking the community to give feedback on how is it that they use it. This information would be very necessary for what we call the CNCF SIG storage team, to provide better presentations, more focused presentations, and prioritize our work so that we can provide even more documents on how is it that storage is consumed and storage is used in a container orchestration system. Next slide. And Sheila?
All right, awesome. Thank you for a great presentation. We do have some time for questions, so if you have questions you'd like to ask, please drop them in the Q&A tab at the bottom of your screen, and we'll get to as many as we have time for. And while I give you a minute to do that, I will plug in here that Kubecon and Cloud Native Con North America is CNCF's flagship event, and it will be here before you know it. This year, it's being held in San Diego, which should still be sunny and lovely in November. This is the time for the community to come together to further education and to advance cloud native computing. Please go to kubecon.io for more info and lock in your tickets before it sells out. So with that, I'll pass the mic back over to you for the questions.
one of the questions about the slides, and the slides will be available with the presentation. Where would the slides be available exactly?
Hi, this is Kim. They will get posted to the CNCF website this afternoon, both the video and the slides. And then the video is also on our YouTube channel, the CNCF YouTube channel, in the webinar playlist.
Excellent. We have another question on podding cluster A using PV from NFS or AWS EFS. For some reason, we are moving the pod to cluster B. I'm guessing clusters are Kubernetes clusters, and the NFS remains the same. Do pod get its own PV and attach automatically? Okay, so in this situation where you're going from one cluster to another cluster, you may need to manually create a PV to describe that NFS mount point location. So then that way your NFS PVC can then mount it. You can also, I don't know if I remember if it's still available, but you can do what's called inline access to storage systems in Kubernetes, where your pod itself has a section in it where you can describe the storage system you want to use exactly. So your pod can have the NFS and the NFS mount point that is trying to use directly in it, and that'll probably be the simplest model if you're going to go from cluster A and cluster B, because that way your information travels with the pod spec instead of being in a PVC storage class style.
Yeah, it's probably worth pointing out that things like that sort of activity where PVs or storage resources need to be shared across different clusters is probably something that is being worked on as part of Kubernetes Federation projects, but it's very embryonic at this stage. So some of the options like Luis just described are probably your best bet right now.
We also have another question. It was mentioned that encryption is possible. Is that for the application to do? And what about authentication of storage? How to avoid unauthorized people read the data? That's excellent questions. There's actually two questions in it, but that's excellent. I'll try to answer it, and others can join in after. First is encryption. Encryption can be done at the storage system. The application doesn't have to do that. Many storage systems have encrypted stores, encrypted volumes, and some of them even have the ability to have your own keys. So you provide your own key model, and they can then encrypt it with those models. So then you are completely protected by providing your application is the only one that can access that data. The second part is on who can access and authentication authorization. That is done by some storage systems, and again, that is done by models where you can, for example, in Kubernetes, you would place your token or your authentication model into a secret, and then the driver for CSI and so on will take that secret information and pass it over to the storage system to authenticate the caller who's trying to use the volume or delete it or create and so on. So Kubernetes doesn't itself stop you from doing that. It is definitely storage systems use the primitives of Kubernetes like secrets to be able to achieve that. Go ahead.
So just adding on a little bit to that. So obviously features like encryption can be employed at different layers in the stack. It can obviously be done at the application level, but as Luis said, most storage systems will support a level of encryption. And this could be done sort of for data that's in transit as well as data that's at rest. One of the key things with all encryption on storage systems is you need to have a good understanding of how the keys are managed, because ultimately a lot of the security is going to come down to where the keys reside and who has access to the keys. So that is something to look out for, especially if you're using different service providers that are managing the keys for you. In terms of the access models, this is where some of the differences between different cloud native storage systems come into play, especially when they integrate into orchestration environments. So, if a storage system has been designed to present storage to individual hosts or VMs, for example, then a lot of the access model will be down to which host can access that data. But in some of the newer systems, you have functionality where access models can be integrated into the orchestrator model. So concepts like the Kubernetes namespaces, for example, and the users and groups model and policy model in Kubernetes can be translated into the security model for the storage system too. So that's one of the things that's worth looking out for.
Okay, excellent. Let's take another question. Is there an argument that a stateful application is a bad use case for containers? Ooh.
Let me take that one.
Yeah.
So there are, as with anything, there are pros and cons. I think it's fair to say that the starting assumption point is that every application needs to store state somewhere, and then what you need to work out for yourself is whether you want to store the state in the cluster, or you want to store the state outside the cluster. And by outside the cluster, I mean using external services or external components which aren't managed by the cluster. And if you look at this in a sort of in a step-through process, if you look at containers as the way of making your application portable and giving you the ability to run your application in more than one environment, because you kind of package all of the dependencies that your application needs into that container format, and then you look at Kubernetes as your way of both abstracting away your infrastructure by giving you a declarative way of describing how your application should run and letting the orchestrator figure out where your application should be positioned. Well, then, you're effectively solving a whole bunch of scalability and composability and automation for your application by putting that into Kubernetes. And the question you need to ask yourself is, do you want your stateful requirements to have that same automation and that same scalability and that same composability? So in much the same way that you declare in Kubernetes what your application needs in terms of network ports and CPU and memory, you probably also you should be able to declare, just like all the other resources, what your storage requirements are in the form of storage classes like Louise mentioned. And effectively, you now have a way of picking up your application and running this across different platforms, whether it's different cloud providers or different on-premise clusters, etc. So if you want to really use the full potential of Kubernetes and take advantage of all of those composability, scalability, and automation capabilities, then I'd say the answer is yes. Of course, I'm slightly biased, but it's still true.
Yes, and actually, I'd like to add to that a little bit. And that question comes a lot because of a little bit of history. Containers and Docker, when it first started, it was mainly focused on stateless or applications who didn't have the state attached to it so much. So because of that model, that idea has continued or tries to continue through. But the reality is that the Kubernetes, DCOS, and other orchestration systems have a very good model of managing state. And because of that, it's quite mature actually at the moment. I remember when I think it was version 1.4 or 1.3 of Kubernetes had just started with dynamic provisioning. Now we are version 1.13. We have CSI. state is quite a mature model now to be able to be managed by Kubernetes. So I would say absolutely that we are in the age now where a state can be definitely managed by Kubernetes. So, all right, let's take another question. Can we thin provision storage for containers? The answer for that is yes. That all depends on your storage system. When you create a volume, that storage system may have thick provisioning or thin provisioning. That is all managed by the storage class, which has these parameters that may be defining what type of storage is the storage class. So, in other words, the administrator creates a storage class with a set of parameters and names that storage class, and that storage class defines how the volume is going to be created. And in there, the parameters would be to either thin provision or thick provision. Again, that's all for the dependent on the storage system. Anybody want to add to that?
No, I think you covered that.
Excellent. All right, let's get another one. What will be good if we want to mount same volume in pod, PV or storage class, if we're using different clusters? Okay, again, this is again a different cluster question. So let's say that we have 2 Kubernetes clusters, we have 2 pods in each Kubernetes cluster, and they want to mount the same volume, I'm guessing. In that model, you would almost need to manage that yourself because the Kubernetes systems, again, are not talking to each other, or unless just like Alex said, we talk about federation, which is something in the future. But you will need to mount probably over some type of file system because you're mounting the volume in 2 different places, and then you would need to manage it yourself. There may be a storage system where you can mount it, through the storage system by you creating your own APIs to it, and then telling the storage system to do, attach it on both ends. You may have to create your own controller, and we didn't talk about operators, but you may create your own operator to be able to manage this and attach it to 2 different clusters. But that is something that's not done by Kubernetes at the moment. Okay. All right. Anybody want to add to that? Okay, let's take another question. These are great questions, guys. Please keep them coming. Who is responsible to erase or delete the content of a volume, or delete the volume in case the volume and the data is no longer needed? Is that in CSI function? Okay, so
do you want, is Xing around to answer that?
Yeah, definitely.
Okay, sure. So there is actually there's a deletion policy that you can set. So when you delete a PVC, if the policy is delete, and then the content will be deleted with it, and then the volume associated with it on the storage system will also be removed. But if it's a retain, then the content and the volume will be kept, and then it's up to the admin to handle that afterwards. So if you are doing dynamic provisioning, then by default, the policy will be deletion.
Excellent. Thank you. All right. Anyone, Alex, you want to add to that or no?
No, not really. I mean, it's in summary, there is a delete policy which can be applied, but ultimately it's either the admin or the deletion policy will trigger the storage system to do the actual delete process, and it's kind of storage system specific in terms of how the content is erased as part of that deletion process.
Cool. New question: can the service in different namespace, can it be accessed by the same PV? So, Xing, you want to answer this one? You've been kind of working on this
yeah.
too.
Sure. Well, actually, this The screen keeps moving. Yeah. So once the PV and PVC is bound to each other, so basically then you are basically, as Luis pointed out earlier, it's like one-on-one relationship, right? You can't really have a different namespace that is associated with that PV anymore because it's bound with this one PVC that is in this specific namespace. Unless if you unbind it, you can use it later by a different namespace.
Excellent.
And there's actually some work going on, like the
cloning.
Well, the cloning is not. The cloning is still limited to the same namespace, but
Okay.
there's also for I forgot what's the code. And there's a feature that actually right now is being designed that allow you to transfer the namespace from one to another, but it's still not shared. But basically, you have to say transfer, and then when the reception side say accepted, then it's going to be transferred. It's still not be shared. So I think this probably is something that could be have something going on in the future. Maybe there'll be it could be possible in the future, but right now it is not. So you can only have like one namespace.
Okay.
Right now, yeah.
Okay, excellent. Here's another question: is it necessary to create a PV before creating a PVC? Alex, you want to take that one?
So it's probably just worth clarifying the terminology. So
Yeah.
PV is the actual volume itself, whereas the PVC is the link that's used during the dynamic provisioning process to link, and it's the reference that the application or the pod is using to refer to the PV. So the PVC creates a PV as part of the dynamic provisioning process.
Yep.
Yeah, so actually for static provisioning, you can actually have a PV first, and that is associated with your volume that is already created on your storage system, and then you can do a static binding to create a PVC to bind with that. Yeah, that's also possible.
Yeah, way back in I think it was before 1.4 when dynamic provisioning came in. The only way to get storage was to pre-allocate a pool of PVs, and the PVC will find the best fit. And that logic is still there today. So that's without dynamic provisioning. So, but normally today when we talk about storage and Kubernetes, we always mean dynamic provisioning to be a dynamic system where storage gets consumed and released on demand. So, and for that, PVCs come in first.
Great.
Right.
Well, thanks everyone for a great presentation. That is all the time we have for questions today. Thank you for joining us. The webinar recording and slides will be online later today, and we're looking forward to seeing you at a future CNCF webinar. Have a good one.